This is the heat-seeking missile, and inside this cover is the optical guidance system. The heat source from this aircraft travels through a set of lenses into the reticle, which spins on its axis. These infrared signatures are converted into audible tones like this sound here. All said and done, the pilot releases the missile, which uses a solid fuel rocket as the motor to chase the infrared heat source. The servo section controls the 4 canards to guide this AIM-9 Sidewinder towards the target. We will also be looking at a super simplified process of how this infrared heat source hit this mirror, filtering the environment light from the heat source. And not to forget the newer version, the AIM-9X missile, its ways and process of tracking an enemy target, all in the video ahead, so stay tuned and don't miss a beat. The AIM-9 is one of the oldest, least expensive, and most successful air-to-air missiles, with an estimated 270 kills worldwide to date. The first successful kill recorded in combat by a heat-seeking missile was an AIM-9 Sidewinder on September 24, 1958. This occurred during the Chinese Civil War when a Taiwanese F-86 Sabre shot down a communist Chinese MiG-15 using AIM-9B supplied by the US Navy. Another more interesting story. During this conflict, one AIM-9B struck a People's Liberation Army Air Force MiG-17 without detonating, enabling the pilot to safely bring the aircraft back to base. This missile was passed to Soviets, who examined it and were stunned by the innovative weapon system. The Soviets used this missile to reverse engineer their own copy of the Sidewinder, dubbed the Vimpelt K-13 or AA-2 NATO reporting name. This marked one of the first transfer of technology that took place during the Cold War era. The guidance and control section consists of the following 3 major assemblies: an infrared seeker assembly used for detecting the target, an electronic assembly used for converting detected target information into tracking and guidance command signals, a gas servo assembly that includes a gas generator, manifold, pistons, rocker arms, electrical solenoids, and thermal battery. This assembly converts electrical guidance commands into the mechanical movement of the control fins. 4 control fins mounted on the guidance and control section to provide aerodynamic lift and course alterations to the missile during free flight. These movable surfaces are electrically controlled and pneumatically operated by this gas servo assembly. This is the missile's umbilical cable is also attached to the guidance and control section. The umbilical cable provides the necessary path for the exchange of electronic signals and cooling gas between the missile and aircraft before missile launch. Let's dive further into the details regarding the heat-seeking missiles and how it works. The front end of the missile was made out of a glass lens instead of a steel-shelled warhead. One of the most important devices is this reticle seeker, a common optical system design employed in conventional heat-seeking missiles. It consists of several basic parts to make this work: a primary mirror, an IR detector, a reticle, the plane, and a secondary mirror. The most simple form of reticle has 2 parts on it, one half transparent, the other half opaque, arranged in this form. This is how it works. The heat source travels through a set of lenses into the reticle, which spins on its axis, and the axis itself rotates in circles. An infrared light will blink at this point marked as located here. This would trace out a path with respect to the reticle axis, generating a signal with varying phase and amplitude. If the jet switches direction to the left, the IR seeker will appear on the opaque part of the object. Let's dive further into this mechanism. A key component of the seeker head is a dichroic filter, which is used to isolate and pass through the required infrared wavelengths. The sensor would see the infrared source only during the transparent portions of the reticle, and so the output of the sensor will be a periodic pulse train of some frequency that is equal to the rate at which the reticle spins and times how many transparent spaces it has. The pulse will then create an audible tone like this one if the missile is in its sight. On the contrary, the Arrow 3 missile uses a pivoting seeker, capable of rotating on each side, thus allowing for extreme lead pursuits, flexibility, and engagement of threats. But it requires a $1 million radar to help track and aim this kill vehicle. The radar sends uplinks to update the new target position and estimated interception point. The kill vehicle adjusts its trajectory using highly dynamic thrust control while aligning its electro-optical sensors towards the target. As stated, this heat-seeking missile is being upgraded to the AIM-9X for decades to come. As you can see, it looks a bit smaller compared to the older AIM-9 versions. When placed side by side, you can see that the back of the AIM-9X has a thrust vectoring system, while the older version has a fixed nozzle. The AIM-9X missile has fins that can pivot independently, whereas the older version has rollerons to maintain stability. However, it is important to note that the AIM-9X incorporates many AIM-9 legacy components, including the rocket motor, warheads, and active optical target detectors. Despite this, its performance far exceeds that of the legacy Sidewinder. It has a solid propellant rocket motor with a length of 9.9 feet, which translates to around 3 meters, and a launch weight of 186 pounds or 84.3 kilograms. Its range and speed are still classified, but it is assumed to have a range of 35 kilometers, translating to around 21 miles with an astonishing speed of Mach 2.5. Let's take a simplified version of how this works. Step 1. In this older version, the pilot needs to chase the target and can release the missile only after hearing the sound peak at a maximum, just like this audio here. This is generated by the reticle optical from the infrared heat signature generated by the enemy jet. Step 2. The missile will initiate the solid rocket motor to launch towards its target. Step 3. Remember the rollerons on the tail, which are metal wheels with notches cut into them. As the missile speeds through the air, the wind current spins the rollerons like pinwheels. These rollerons on the rear wings help stabilize the missile in flight, acting as gyroscopes to counter the spinning forces. Step 4. As stated, the servo pumps and pistons work their magic and move the canards to compensate for the target's evasion from the center. Step 5. The missile is designed to overcompensate for the movement to where the target is vectored instead of chasing the aircraft. As stated, the rollerons are designed to maintain a steady trajectory for the sensor as shown in this animation. Step 6. When it reaches the target, the proximity fuse triggers the 9.36 kilogram or 20-pound annular blast fragmentation warhead. This explosive force propels the metal fragments outward in all directions in an annular or ring-shaped pattern, destroying any aircraft when it is launched against it. However, sometimes it could lock onto the sun or another heat source instead of an enemy airplane, such as a plane deploying flares. Later on, the AIM-9X began using infrared cameras to take pictures of where the seeker head is looking and again, use computer algorithms to find their target. The difference is that IIR seekers can recognize the shape of an aircraft and compare it against a database, using that information to improve their ability to track the target. Once locked, it can avoid flares and hit its target successfully. Check out the Boeing B-52 bomber, the Bradley infantry fighting vehicle, and many more original videos just for you. So please hit the subscribe and like button.